Hello, welcome everyone. Today we'll continue with chapter 9, 9.3 onwards. So let's start. Look at this figure. This is for base bias amplifier where we are applying AC input. Whenever we apply the AC voltage here, the AC voltage VB will be available across the base and it will proportionately create AC output current, that is IE here. So we want to study the small signal operation of amplifier. So look at this figure. This is a graph of current IE versus VB. Whenever the input voltage is given to the base bias amplifier, when AC input is coupled, your VBE will vary like this. There is an AC variation in VBE like this. This is the graph of your Q point. This is the Q point, your DC Q point. But you know that your VBE now will be a combination of AC plus VBE is now a combination of AC VBE plus DC VBE. That is a total VBE. So this is your DC Q point. Whenever the AC voltage is coupled, your when the positive half cycle is there, your VBE will increase like this, and when there is a negative half cycle, your VBE will decrease like this. So it will move up to this point and it will go up to your Q point will go higher. In negative half cycle, your Q point will come down. Proportionately, uh, the AC voltage on the base produces the AC emitter current, okay, of the same frequency as the AC base voltage. So the suppose the frequency of the input AC source is 1 kilohertz, then the frequency of this AC current will also be 1 kilohertz. But see the effect here. When in the positive half cycle, due to this curvature of this graph, when there is a positive half cycle, you can see the positive half cycle of your current is elongated, and in the negative half cycle, the negative half cycle of the current is shrink. So this is compressed and this is elongated, expanded. So this frequency of input voltage source and frequency of output voltage source will be same, but the output current will not be the exact replica of the input voltage source, but it is slightly distorted. So this is called distortion. This elongation and this compression is called the distortion in AC signal. So how we can reduce this distortion? Of course, this distortion is undesirable. High frequency amplifier, because of this, it will change the sound of voice and music. So it is undesirable. How we can reduce this distortion? So we can keep the AC base voltage as small as possible. The smaller the swing or the variation, the lesser the curvature in the graph, and the small signal, the graph will appear to be linear. So that we can see in the next slide, if we consider that your AC variation is very small here, 1 milliampere peak to peak, that is our AC variation. If your variation in AC is very small for this region, then we can say that we can consider this as almost a linear portion, and the curvature, very small part of the curvature is included. So we can see that we are getting up here the graph as a linear graph. So the total ammeter current shown in figure 9.10 here, the total current IE in figure 9.10 will be a DC component plus the AC component. So your IE is equal to IEQ plus IE, that is a DC plus AC. Meanwhile, we are writing capital EQ, that is capital EQ indicates the DC current, and Q means quiescent point, and I small e indicates the AC quantities. To minimize the distortion, the peak-to-peak value of I must be small compared to IEQ. How much small? So we consider a 10% rule. So the AC value should be 10% of the DC value. So IEQ peak to peak should be less than 0.1 of IEQ. So if the value of IEQ is 10 milliampere, then we will consider this peak to peak value is only 1 milliampere. So for now onwards, we will refer to the amplifiers that satisfy 10% rule as small signal amplifiers, and they are available at the radio and television receivers. So that you can see here, the variation here, the DC ammeter current value is 10 milliampere, then this peak to peak variation will be only 1 milliampere peak to peak. So if a transistor follows this 10% rule, then we know that the variation in beta, variation in Q point due to this change will be not much, and we can reduce the distortion. Now look at one example using the same. This is the TACB amplifier with the waveforms, and you want to find out the value of IEQ peak to peak. What can be the maximum value of AC current IE peak to peak? So for that we need to find out the DC value of I. So that we already know how to do the DC analysis. We can find out 1.3 milliampere, and by keeping 10% rule, this will be, if it is 1.3, it will be 0.13. Now comes the next topic is AC beta. Till now we have discussed the DC beta, that is DCIC upon DCIB, that is both the DC currents. Definition of AC current will be IC, AC current IC and AC current IB. This is the Q point, the graph of Q point. Your beta of DC beta will utilize the complete graph based on the location of Q point. If Q point here, Q point can be anywhere on this graph. But if you look at the AC beta, then if we assume the Q point here, then it will utilize only this portion for the AC beta. Graphically, beta, this beta indicates the DC AC beta, and whenever we want to indicate the DC beta, we will write beta DC, and if we write simple beta, that means it is a AC beta. Graphically, beta equals the slope of the curve bias the transistor to a different Q point. If we were to bias the transistor at a different Q point, the slope of the curve would change, which means the beta would change. In other words, beta depends on the amount of DC collector current.